Okay, the purpose of this podcast is to introduce us to integration, which is another way of stating anti-differentiation. We speak about the integral of something like x to the n, and you will have this new notation entering into your life. You can see lots of references to it, and the sooner we start using it, the better. So introduction to integration involves just the basics of kind of working from a differential form back to the actual function form in question. Some contexts for the topic, and we'll see this developing in subsequent podcasts, would be dealing with areas under curves, between curves. There will be such standard integrals that we'll be talking about. Again, here's a reference to something to do with an area once again. So all of that is coming. It's not the purpose of this particular podcast, but it's on its way. So to get things started, if you were asked, or at least given, that f prime of x, for example, is equal to x squared, and more or less asked to work backwards to come up with the function itself, if you had to think about that, you might start thinking about, well, what degree form would the function have to take in order for its derivative to be of degree 2? And if you start having a play and working backwards, you might end up stumbling on the fact that there needs to be some kind of an addition by 1, and then, as it turns out, a dividing by that. So this idea of since the x to the n power rule for differentiation required n times x to the n minus 1, since there was this n minus 1 feature, there's something about adding the 1 back. So it's not surprising, and it would not be too difficult to arrive at this kind of result here. So, however, just stating that f of x is equal to 1/3 of x cubed would not quite be good enough, even though the derivative, of course, of 1/3 x cubed would be the x squared in question. There is the possibility that there could be an infinite number of constants, or this so-called constant of integration, or arbitrary constant, which just means a random constant in terms of this being lifted by some c or decreased by some c, directly in a transformations sense. We'll come back to that in a second graphically. So generally speaking, a good idea in this context is to be moving away from this representational form of a derivative and actually using your dy dx type form, because you will have the advantage, especially in very difficult settings, to split the operators. You can multiply both sides by dx, and then you take the antiderivative of both sides, or in other words, the integral of both sides, because if two things are equal, their antiderivatives are also equal. And this begins to communicate what you're trying to establish. And of course, the antiderivative of the derivative of y, that's kind of like one step forward, one step back, leaving you with just y itself. And so starting to embrace this kind of notation, being comfortable with it, using it, reading it, that's going to matter. Again, we can split the operators, not something arguably in context here that's so necessary in terms of the simplicity of this result, but we will find as we proceed that it can be a very nice way to attack problems, because these differential operators will be communicating something to us quite specifically. So let's take a look at an example, a kind of a classic example. Excuse me, and let's determine the function f of x of a curve passing through a particular point that has this derivative. Super standard type of an application of a derivative. So let's switch, like I said, the notation over to dy dx. We'll split the operators, and then we'll take the integral of both sides. And so I would like you, again, to be getting more and more comfortable with this kind of notation. So doing all of this process by way of a method is not necessarily required, but appreciating that this form here can be re-represented in this integral form here is quite useful. So that you're being asked to integrate these two variables with respect to x. That's what that's actually saying to you. And of course, the power rule just says, add 1 to n, divide by that, add 1 to the 1 here, divide by 2, and of course there's this plus c. I've referred here to a so-called family of curves, and what you can appreciate here is that whatever this looks like, this cubic in space, it could be lifted up by some c or dropped down by some c. So there is literally an entire family of curves, and we'll see that with the visual in the next slide. However, you know that this function has to satisfy the given point, so there's only one curve in particular that actually owns this point. By virtue of letting x be 1 and y being f of 1, and actually trying to isolate the constant in question, you'll pick up that the constant is negative 1/2. So therefore, this is the actual function that satisfies the action of what's being asked here. And that would be some kind of cubic, as it turns out, just dropped down by negative 1/2. And the darkened version of what you see here is precisely that function. So the entire family of curves, which would be just this piece here, plus or minus some c, we've nailed down the specific one that of course goes through the point 1, 1, that's right here, and that actually accounts for the final answer. So, quick reminder about kinematics. We've seen a kind of a left to right version of this, and now we'll be talking more about a right to left version. So namely, if the displacement function, which is often a function of time, provides us that the velocity is its rate of change or its derivative, that's the ds dt thing going on, and then the rate of change of the rate of change is better known as the acceleration, that's our second derivative, and there it is there, the d dt of this form here, of this form here, will give us d2 ds, d2s d squared of the actual representational form of the acceleration. So we now are in a position to be able to not only, in a differential calculus sense, work from left to right, but now we can work with these functions and start to work backwards from right to left. So here's a classic example illustrating that. I'm a particle moving in a straight line, once again straight line particle motion. The velocity equation is given. T is in seconds after the particle's initial start. So we need to determine the actual displacement function. So we're going to integrate this guy in just a few seconds in its general form. And then in a particular version, given that the particle passes through the origin at exactly this point in time, let's show that the actual constant of integration is what you see here. So firstly, to find that displacement function, the velocity is a function of time, and that suggests that the displacement function is the integral of v dt, and that looks like the integral of v dt in this form here. And so working backwards, of course, from this form, not too challenging. We know that if the sine's derivative is the cosine, then of course the integral of the cosine is the sine, and that is something that's highlighted for you in your formula booklet. And then working algebraically on this piece here, using a kind of an algorithm that we've already established in terms of how to deal with a polynomial piece, that ends up giving us that the displacement function as a function of time looks like what you see here, and our task is of course to find c, or to show that c is equal to this given that the particle passes through the origin at precisely this point in time. So its position of course will be during the time of pi over 2 seconds. It's exactly at the origin. So this point of course needs to satisfy this displacement function, and when you play out the mechanics of that, we get something like 1 over pi over 2, which of course is just a negative 1 over that, which of course is a negative 2 over pi, and so we can actually establish that we have the integration, the constant of integration established as requested. That's pretty much it for a warm-up. Hope that was helpful. Bye.